Hey guys, how was your weekend? Good to hear. Me too. We're going to be doing tangent lines to circles. All right, I made a video answer key to some of the homework questions that was due today. So take a look at that if you had trouble with the homework. As always, ask me any questions. But today, tangent lines. So a lot of definitions I know for circles to start out with. We define central angles, arcs, chords, right, radii, etc. Today we are going to be defining a couple more things, including what a tangent is, which I know a lot of you already know. So let's draw a circle. And a tangent is a line which intersects the circle in how many places? All right, very good, class, in one place. So that, for example, is a tangent line. It touches the circle exactly one time. So tangent, that is a line which intersects a circle in exactly one point. All right, what do we call a line if it intersects the circle twice? So something like this would intersect the circle twice. And that is called a secant line. So secant, that is a line which intersects a circle at 2 points. And I can just copy and paste this. And I'm going to change the word 1 to 2 and get rid of the word exactly. So a line which intersects a circle in 2 points is called the secant line. And so we already know a tangent is a line that intersects the circle once, right? So there's the 1 point, right? That's our point of tangency. But could we have another line that intersects the circle once at this point, right? Could I draw like a tangent line like this? No. Well, could there be more than one tangent line there? Well, I didn't draw that really well. But you can imagine if I try to draw any other line, right, it's going to pass through multiple times. There's actually only 1 point, or only one line that passes through this point that's tangent to the circle. Right? Any other line I try to draw going through that point, it's going to intersect somewhere else. Right? I'll try to draw this. So if I take this line, right, and I start rotating it around there, you can see it intersects 2 times, 2 times, 2 times, 2 times, right? Even when it gets really close, it's still intersecting 2 times, just really close to each other. There's really only one line where it only intersects once, and that's this guy, right? Everywhere else, it's going to intersect multiple times, right? Hopefully you guys can see that. And don't try to cheat me and say this line intersects once as well, right? Because of course we know lines extend infinitely in both directions, so that is a secant line. So an important note about tangent lines, which we just talked about, is that at a given point on a circle, there exists only one and only one tangent to the circle. Right? At a given point on a circle, there is one and only one tangent to the circle. So wherever I put a point on the circle, there's only one possible tangent line. And there it is. Over there, there's only one possible tangent. There it is. You can't draw more than one, right? You can draw other lines that might look to be tangent, right? But there's really only one possible tangent line. So these tangent lines, they're pretty special because in this first lab, we're going to see something about it. So lab number 1, let's construct a circle, construct a radius, and construct a perpendicular to the radius at the point of intersection. Okay, so get your calculators, read through the steps of this lab, right, and try this on your calculator. All right, this one is not too bad, so hopefully you're able to do this. I'm going to be opening up Sketchpad on my computer now, and let me share that with you guys. So I'm going to be doing this on Sketchpad. Again, I'm sorry I don't have access to a calculator, so this is the best I can do. So on your calculators, hopefully you have a circle, right? Draw a radius in, so just go from the center to any point on the circle, and I think it paused. All right, there we go. Construct a perpendicular to the radius at the point of intersection with the circle. So on your calculator, you're going to click the radius, you're going to click this point, right, and you're going to construct a perpendicular line. And good. Now, next, drag the point around. What can you conclude about a line that is perpendicular to the radius, or to a radius? I missed the word to there. So if I move this point around, wow, you can see this line that is perpendicular to the circle is also tangent to the circle, right? Because it's only passing once. That's the only point of intersection. So pretty simple theorem. But if we go back to our notes, why don't you guys fill that in, see what you're going to write there. But how do I share again? I have to go back here. And so our theorem says, if a line is perpendicular to a radius at its point of intersection with the circle, then the line is perpendicular. Or sorry, then the line is tangent. We already know it's perpendicular, that was the given. All right, if a line is perpendicular to a radius at its point of intersection with the circle, then the line is tangent. So all of these tangent lines I drew over here, these are actually perpendicular with a radii, or any radii. And there's no tangent line here, so let me draw one in. Boom, that's what that theorem is saying. Right, so the converse theorem is what you get when you switch the hypothesis and the conclusion. So our hypothesis was what happens if a line is perpendicular to the radius at its point of intersection with the circle. And the conclusion was that the line is tangent. So our converse theorem is that if a line is tangent to a circle, then what must be true? Then it is perpendicular to a radius. So there's only one radius that it's perpendicular to. So I say it is perpendicular to the radius that, or to the radius, I'll say drawn to the point of intersection. Change the color of that. So if a line is tangent to a circle, that tangent line is going to be perpendicular to the radius drawn to the point of intersection. Right? So important theorem, tangent lines are perpendicular to the circle. So, all right, lab number 2. Let me go back to Sketchpad. And let's take a look at lab number 2. This one is also a quick one, right? Also something you can do on your calculator. All right, so construct a circle. Construct 2 radii on opposite sides of the circle, right? I know a circle has technically no sides, so just don't draw them like this close, right? Draw them on opposite sides, however you want to take that to mean. I think the screen was paused before, so if you can't see that, I'm sorry. But draw 2 radii like that. Construct perpendicular lines to the points on the circle where each radii intersects the circle. So it's the same thing we did in the last lab. We were just doing it 2 times now. So I'm going to construct a perpendicular to that point. Construct perpendicular line. Construct one here. Construct perpendicular line. So on your calculator, you might need to drag the ends of these lines so that they intersect. So let's mark that point of intersection over there. Measure the distance from the external point to each point of tangency. Move stuff around. What do you notice? So here's our point of tangency. I'm going to call it point A here. What did I call that point? Did I call this? Sorry. Here is the point of intersection, the exterior point of intersection, right? And here are our points of tangency, B and C. Here's the center of the circle. Let's call this circle B. And measure the distance from the external point to each point of tangency. So I'm going to measure the length of AB. It's 5.49 centimeters. And what do you think the length of AC is going to be? Wow, also 5.49. All right, move stuff around. What do you notice? So as I move, let's say point B there or point C, right, we see the distances from our external point to the points of tangency remain the same. Wow. And this would even work for a major arc, an arc more than 180 degrees like BC, right? The external point of intersection would just be on the other side. So that obviously makes sense. The only case where this would not work is if this were a diameter, right? So I can't get this exactly to be a diameter because, yeah, it's too precise for me. But you can see if CB were a diameter, right? These would extend forever because they would both be perpendicular to the same diameter, and so they would be parallel and never intersect. But everywhere else, we're going to get a point of intersection, and those distances are going to be equal. So we're going to prove this one Euclidean, which is nice. Got a nice proof coming up. All right, so theorem, tangent segments drawn to a circle from an external point are congruent. All right, if you have some external point B, and I drew in 2 tangent lines, right, these distances, AB and CB, are going to be the same. AB is congruent to BC. So given, what are we given in this proof? We're given 2 tangent lines. So I'm going to say given AB, right, tangent to circle, what is this, circle B at point A. And I am also given another tangent segment, CB. So given CB tangent to circle B at point C, what are we trying to prove? Well, we're trying to prove that tangent segments drawn to a circle from an external point are congruent. So we got our 2 tangent segments, AB and CB, right, drawn to a circle from our external point B. And we want to prove that those segments are congruent. So prove AB is congruent to CB. So, like all of our other circle proofs, what do you think we're going to construct? Well, we prove things congruent probably using triangles, right? So I don't have any triangles here, so probably be a good idea to draw in these radii, AD and DC. We know those are congruent. And there's another segment that might be good to draw, and that would be DB. All right, drawing that in, now I see I have two triangles. And what kind of triangles are ABD and BDC? Well, they are right triangles because, those are right angles. We know tangents are perpendicular to the radii, right, drawn to that point of tangency. So if those are both right triangles, well, let's see what else we can prove. Well, we can say all radii are congruent, so we can say AD is congruent to CD. Right? I should have marked those up because that's what we're trying to prove. Right? So I deleted those marks. We don't know that, so I can't use side angle side. But I do know reflexive property over here for BD. So we have, again, angle side side, which we can't use, but oh, it's a right triangle, so I can use hypotenuse leg. So once we've proven hypotenuse leg, we can show AB is congruent to CB by CP/CTC. So this is not a bad proof. Let's just write this out with that one new step. All right, so step one are the givens. So let's just copy and paste this. Copy, paste, given. All right, step two, we're going to construct some radii. So construct radii AD and DC. Right, reason is between only 2 points, only one segment can be drawn. All right, step three. What do you want to make step three? I guess I'll make the radii congruent first. AD is congruent to DC, or say they're congruent first, I'll make them congruent. Right, and of course they're congruent because radii of the same circle are congruent. Step four, let's use reflexive property next for DB is congruent to DB. And now we have to say they're right triangles, so let me call this angle 1 and angle 2. I'm going to say, before I say those are right angles, I'm going to say AB is perpendicular to AD. All right, so AB is perpendicular to AD, and BC is perpendicular to DC. So why is that? What's the reason for step 5? Well, that was the first theorem we talked about today from our first lab. And that theorem says, well, actually it's the converse theorem. If a line is tangent to a circle, right, then it is perpendicular to the radius drawn to the point of intersection, or to the point of tangency. I actually like point of tangency better, so I'm gonna place that intersection symbol with tangency. So a line tangent to a circle is perpendicular to to the radius drawn to the point, of tangency. All right, a lot to write out. First time we've used that theorem, of course. But now that we know these are perpendicular, we can say angle 1 and angle 2 are right angles. Or right angles. And now we can use hypotenuse leg. And of course, angle 1 and angle 2 are right angles because perpendicular lines form to intersect to form right angles. Step 7, I should say the triangles are right triangles. So how should I name these? I'll call it ABD. So triangle ABD and triangle D. No, I said ABD, so CBD are right triangles. And now I can use hypotenuse leg. So triangle ABD, congruent to triangle CBD, my hype leg. And finally, step 9. What we're trying to prove. Trying to prove this. Now you can prove that those two are congruent by CP/CTC. All right. So not a bad proof, but now we've shown that to be true. All right, that tangent segments drawn to a circle from an external point are congruent. So corollary theorem, if two tangents are drawn to a circle from an external point, the line determined by that point and the center of the circle bisects the angle formed by the tangents. So that's a mouthful, but again, it's saying if two tangents are drawn to a circle, then this line over here, DB, is going to bisect the angle formed by the two tangents. In other words, these two angles are going to be congruent. All right, so this is a corollary theorem because it's derived from another theorem, which is this theorem. So based on this theorem, all we have to do is add one more step, or based on the proof to that theorem. Right, we only have to add one more step, which is that angle 3 is also congruent to angle 4 by CP/CTC. Right, so it follows, right, corollary kind of means like it follows from another theorem. It follows that this is also true, right, that DB is going to bisect the angle formed by the two tangents. So 2 properties you need to know, actually 3 by now, right, but first, just to recap, if you have a circle and you draw a line tangent to it, that is going to be perpendicular to the radius drawn to that point of tangency. Well, if I pick an arbitrary point on the exterior of the circle now, and I draw another tangent line from that point to the circle, boom, that of course will also be perpendicular. But now we've proven that these two distances from the point of tangency to the exterior point are congruent, and we also know that that segment from the center to the exterior point bisects that angle. All right, so let's use this to answer some questions. These questions are going to be a lot easier than what you see on the homework. All right, but it's the same ideas, just applied in different ways. All right, so let's take a look at these 2 examples. Given points H, I, and J are points of tangency. JG is 8. HF is 11. Find the length of CB. There is no CB. I did not mean CB. What did I mean?